All right, folks. So, looking at a new video here, we're getting started uh, learning some rules that are going to let us compute derivatives a lot faster. So the idea is that now we're going to compute these and not have to rely on the limit definition. So that's what we're saying here. If possible, want to avoid explicitly evaluating a limit every time. We've seen that. We're very good at it now with all the practice. But it's kind of time consuming, certainly not very efficient. So if we can figure out a faster way to do some of these computations, some of these common ones especially, we can save ourselves a lot of time and be able to handle a lot of different functions, which is a good thing for us. So that's what we're looking at in this chapter that we're just starting here, and in the upcoming videos, that's what we'll see. So the first one, real basic one, the derivative of constant function is the zero function. So if you were to think about, just real quick, you got a function there, constant function. Just think about at any point along there, the tangent line is coinciding with the graph of that function, right? And the derivative, well, it's just the slope of the tangent line at every point. It's the same slope everywhere because the tangent line is that graph. And that horizontal line slope is 0, so that kind of makes sense. So thinking about the graph is really helpful with that. So nice easy rule to get us started, nothing too crazy. A couple examples: constant function, constant function. Sometimes it can be tricky if you're kind of forget that these are constants, but really straightforward rule there. This one's the big rule, probably the biggest rule of what we're going to talk about today, and something that gets used really a lot. So it's called the power rule. Some places will call it something like a general power rule, or there's variations on that. I'll just call it the power rule. So what it says is if you've got a function that's just a power function, just your indeterminate, your independent variable raised to a power, where n is any real number, so it's the type of numbers we deal with, positive whole numbers, things like 2, 3, 127, negative integers, negative 10, negative 25, and so on. Rational numbers, so that's an integer over a non-zero integer, 2/3, negative 127 51st, whatever it might be, and then all the numbers in between, things like square root of 2, e, pi, pi squared, pi cubed, and everything like that. So any number you have of the type we deal with, which are real numbers, if you've got x to a real number power, the derivative, you bring that exponent down out in front, it's your new coefficient, and you subtract one, and that is the derivative there. It's a very powerful rule, pardon the pun, but one that we definitely want to have a firm grasp of. So several examples here. Certainly if you just see it like this, x squared, 2 comes down, 2 minus 1 is 1. We don't usually write 1 as an exponent there. You can imagine it's there if you like. Next one, y equals x to the 5.8. Kind of a weird function. But dy dx is going to be 5.8. That coefficient brought down, that exponent brought down its coefficient, and you subtract 1. 5.8 minus 1 is 4.8. Same idea here. What you might do, you might find that writing it in this exponent notation rather than this kind of fraction notation makes it a little easier to use the power rule. So you might, until you get used to it and you start doing it a little bit faster, you might kind of have these intermediate steps of writing it like that. Then g prime is going to be negative 1 times x to the negative 1 minus 1, so minus 2. And then you can write it back in that form there, if you like. Similar thing here. Let me do this color green. You might say h of t is t to the 1/2 to get started. When you're early on doing these, writing that exponent, that power notation, whatever you want to call it. then h prime of t is 1/2 t to the 1/2 minus 1, so negative 1/2. And then rewriting that, it would look like what you've got here. All right? So just want to get comfortable with that rule. It's really, really useful, really important. We use it a lot. So that's one to commit to memory sooner rather than later. The next rule is for a very specific type of function. We'll look at general functions, general exponential functions down the road. So later, we'll look at y equals 2 to the x, y equals 12.5 to the x, etc. There's going to be one rule to handle all those possible exponential functions. But what we have now is just one. So when we say the natural exponential function, we mean base e, where e is at 2.718. So the derivative of the natural exponential function is just itself, which is a really unique property. Basically, if you have a derivative whose a function whose derivative is itself, it could be the zero function, or it's going to be a multiple of this function. It's kind of an interesting thing. A note here, we won't stress it yet, but we will come back to it down the road. In this process of figuring out that derivative, we would have determined or somehow proved this identity here. And that says the limit as h goes to 0 of e to the h minus 1 over h is 1. And you can look in our textbook to get a little bit more follow-up on that. I'm going to leave it here and just say, hey, we used it in the background. You definitely want to remember this formula. And this, is a cool result. Well, like I said, we'll revisit it, but for now it's kind of a little bit of a footnote. Okay. So what we've got now are a couple of what we're calling general differentiation rules. So this, it's not specific to functions of particular form. Like it doesn't have to be an exponential function, doesn't have to be a power function, anything like that. As long as it's differentiable, these rules are going to apply. So the first one is the constant multiple rule. If you know that you've got a differentiable function, if you multiply it by a scalar, multiply it by some number, your function is still going to be differentiable. So for example, we know that this is differentiable because we can use the power rule and we know how to come up with the derivative. So this function is differentiable, and what we would do is just take the derivative of the one we know, x squared, so the derivative is 2x, and then multiply it by the constant. That's what this is saying. It's easy to get overwhelmed with the notation. Don't let your head spin over it. It's really just saying a constant doesn't affect what's going on. The second rule, it's really two rules, but I said some difference rule, just in the interest of space. But you can, if f and g are differentiable functions, you can create two new functions by looking at their sum or their difference. And those new functions are going to be differentiable. And they're going to be defined just in the way that you imagine. So if you had f plus g, the derivative of that would be f prime plus g prime. So example would be something like y equals x squared plus x cubed. We know that individually these are differentiable. We have the power rule. And so what this sum rule tells me is that I can just look at the individual derivatives and add them together to get the overall derivative of this function. These type of rules you're going to use over and over again without really thinking about them. They're important, they work in the background, but we don't generally consciously cite them when we use them. Same idea with some of the limit laws. We don't always think about them, but they're working in the background. They make everything work. So that's kind of what I'm saying here with this example. This is a really worked out example. We've got this function here. If you're doing a careful, meticulous, tedious, whatever you want to call it, application, the f prime is going to be the derivative of this with respect to x. We would start off with sum rule and a difference rule from there to there, so you can look at those individual pieces. From here, we're using the constant multiple rule. And then from here to here, it's the power rule along with the exponential function rule. And then here it's just bookkeeping. Now in practice, what you're going to do is you're going to see this sort of thing with some practice is going to be easy, relatively speaking. It's going to be easy for you. And you're just going to go from this, you can say f prime is that. You're going to bypass all these in terms of writing them out, but this is a very careful application of the rules. Like I said, they're working in the background, but we don't typically write them all out. Alright, so that's what I'm saying here with this slide. They are important, but we use them so often we don't usually even think about them. And this kind of goes back to an earlier thing I mentioned. If you had something like g of x equals 10x squared, you don't think about this as a constant multiple rule and blah, blah, blah. You just jump straight to this. And you probably just say, I use the power rule, and don't even think about the constant multiple rule. Certainly, in practice, you don't write out those steps. So with practice, you'll all be pros at this, and you'll get it pretty quickly. So if you have the power rule, constant multiple rule, and the sum rule, you combine those all together, all of a sudden now we have a big class of functions we can find derivatives of. Namely, polynomials would be in that group, because a polynomial is just what's called a linear combination of power terms, which just means it's a sum of multiples of power terms. So we could do something like these very, very quickly. The individual terms, I guess here we use the constant function rule, but we're using the big rule is the power rule. And then we got sums and differences and constant multiples. And save you the writing there, but if you look at this one, derivative is a constant 0, derivative of this is negative 2, 6x. Boom, got it right there. G of z, this function, you see it as a polynomial, or even if it's not a polynomial, something that I can use. I break it down into the pieces. 3 times the derivative of that, so I wouldn't even probably think about that. It's just say 12z cubed, right there, plus 50z to the 9th, count down by 1 on the exponent. 2 comes down, so that's a 1, z to the 1, so minus z. Constant term here, just a 0. Done. For this function h of x, power rule here, 6x to the 5th. 4 comes down, so 5 times 4, 20 over 3, x to the 3, right there. 2x, the derivative is 2. You really will do them that fast with a little bit of practice. So we're not formally thinking about the constant multiple rule and the sum rule over and over again. We probably are thinking about the power rule a little bit. And last thing to note, just something to think about. What do you notice about the degree of these derivatives? So this one was degree 2. This one's degree 4. This one's degree 6. You notice this one's degree 1, degree 3, and degree 5. And just by inspection, it looks like, 2 to 1, 4 to 3, 6 to 5. So for polynomials, it would look like the derivative is going to be a polynomial function of degree 1 less than the original function. Looks like that's not hard to prove. That is the result. So every time you take the derivative of a polynomial function, you knock it down 1 degree. So just kind of a follow-up question, something to think about there. But that's it. That's all I have to say for, oh, I guess not. I forgot about the last slide. So real quick, we don't have polynomials here anymore, but you can handle this one. One thing you might do to help yourself just a little bit, you can rewrite this as 2x to the 1/2. Write it in that power notation, exponent notation. Do it a little bit faster when you're using the power rule. Here we've got multiplying things together. We don't have a rule for that yet, so I might just distribute, and I would have 2 to the 5/2 minus t cubed. This is 2 to the 1/2, so 2 plus 1/2 is 5/2. So when you do that, you got your power terms, and you can do that a little bit faster. I'll leave that up to you. But what we looked at was the power rule, that's the big one, natural exponential function, and then the sum and difference constant multiple rules. So a lot of tools we can use now.